Hey everyone, it's Nam. So today we're going to talk about coordinate systems. The idea is we're going to try to find some way of taking a vector in a vector space V into some representation in Rn. So more specifically, let V be a vector space, and suppose that V has a basis of size n, and we call it script B, and the vectors in the basis are B1 vector through Bn vector. And just quickly recall the definition of a basis of vector space. Yeah, so a basis is just a set of vectors in V that is linearly independent and spans all of V. Right. So now let's take a vector x in V. The definition of the coordinates of x relative to the basis B, or the B coordinates of x, are the numbers C1, C2 through Cn, such that x is C1v1 plus C2v2 plus dot 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 Cnvn. Okay, so that's the coordinates of x relative to the basis B. And so this gives rise to a vector in Rn denoted x sub b, and the vector is simply the vector c1, c2 dot dot cn. Okay. And note that the order of the vectors in B, you know, how you numerate the vectors in the basis B matters. Let's just say C is the basis B2, B1, B3, B4, dot, dot, up to Bn, right? So nothing changes except for the first two vectors. They switch places now. Then the x sub C, the coordinates of x relative to the basis C there, is going to be C2, C1, C3, C4, dot, dot, up to Cn. Okay, so that sort of explains what I was writing here, that the orders of the vectors in your basis matter. So if you're gonna specify a basis, you fix that order, then you stick with that throughout your calculation. Okay, so why does the definition of the coordinates make sense? All right, so in other words, why couldn't there be another set of numbers, d1, say d1, d2 through dn, perhaps different from the ci's above, such that x equals d1 v1 plus d2 v2 plus dot dot dn vn? Right. In other words, we're trying to figure out if you're going to define something, then you better make sure that it is a well-defined notion, and so so there better be only one way of defining coordinates of a vector x relative to a fixed basis and with a fixed order of the vectors enumerated in the basis, right? And so coming back to our original question, namely, why is the definition why is the notion of coordinates of x relative to b a well-defined notion? And the key is that, you know, this is a basis, and so the vectors in the basis are linearly independent, right? And so why is linear independence important in this definition? So again, let's go back. Okay, so we suppose that there are another set of numbers, d1 through dn, that you can express x in terms of d1 through dn, right? So x equals d1 v1 plus dot dot dn vn. And we also know that x equals c1 v1 plus c2 v2 plus dot dot cn vn from our definition of the coordinates of x relative to b. Okay, so why? So we're gonna argue that C1 has to be equal to D1, C2 has to be equal to D2, C3 has to be equal to D3, etc. Okay, so why is that? Well, subtract one equation from the other, then you see that you would get the following equation: x minus x, which is just the zero vector, equals C1 minus D1 times V1 plus C2 minus D2 times V2 plus dot Cn minus Vn times Dn. Oh, sorry, the last term is Cn minus Dn times Vn. Okay, and the vectors V1 through Vn are linearly independent, right? So this is where we're going to use the definition of linear independence. You got a linear combination of vectors V1 through Vn that equals the zero vector. So in this case, you got C1 minus D1 times V1 plus dot Cn minus Dn times Vn equals 0. The vectors are linearly independent. That means that the coefficients are all 0. And that's the only way this could happen, right? And so that means that we have C1 minus D1 equals 0. So C1 equals D1. And similarly for all the other coefficients, so C2 equals D2 and Cn equals Dn, etc. Okay. Okay, so next. So let's just look at a couple of examples of computing coordinates. So in the example 1, let's just take the so-called standard basis for R2. Right, so our vector space now is R2, and a basis for R2 consists of two vectors, E1 and E2. So recall the definition of E1 and E2, right? So E1 is the vector E1 is the vector 1, 0, and E2 is the vector 0, 1. Let's just take an arbitrary vector x in R2, and the coordinates of x are x1 and x2. And it's easy to see that the coordinate of x relative to the basis b is simply x1, x2. And why is that? Well, because x1, x2 equals x1 times e1 plus x2 times e2. And so clearly the coordinates of x relative to the standard basis is just x1, x2. So now let's take another basis in R2. Call it C, and in this case C consists of two vectors, V1, which is the 1, 1 vector, and V2 is 0, 2. Okay, so you can, I'll leave it to you to check that this is indeed a basis. So you have to show that C is linearly independent and it spans all of R2. We've done this sort of exercises many times before, so I'll leave it to you. So let's take x to be the vector for 3. Okay, so the coordinates of x relative to b is 4, 3, as in the example 1. And if you compute the coordinates of x relative to c, you find that it's going to be 4 minus 1/2. So you can verify that 4 times the vector 1, 1 plus minus 1/2 times the vector 0, 2 equals the vector 4, 3. Okay? So we're getting two different representations of the same vector x relative to two different bases. So in general, the b coordinates of a vector x sort of give the location of x relative to the vectors in B. So for instance, in the example 2 above, x relative to the coordinates of x relative to C, x of C is 4 minus 1/2, and that tells us that you need to go 4 units along the direction of the vector V1, and then you go 1/2 units along the direction opposite to the direction of V2 to reach x, right? But if you represent x in terms of the standard basis, then what you do is you go 4 units along the direction of E1, and then you go 3 units along the direction of E2 to reach x. But it's the same x, it's just that you just represent x in terms of two different systems. Okay, and this sort of ideas has shown up in many places in physics, in engineering, and say in your calculus courses. You might have seen points in R2 being represented by the Cartesian coordinate system or the polar coordinate systems. It's not quite the same as what we're doing here for two different bases, but that's sort of the idea, that you can represent one object in various different ways. Okay. And so here's the picture that I ripped off on the internet about on this topic. And so you can sort of see that your x vector here is this black arrow, and then the so there are two different bases. So we are in R3 now. So there are two different bases, the red ones and the blue ones. So then the coordinates of this black vector x will be different depending on what basis you choose. Okay. All right. So here's a basic problem that is relevant to us, and the basic problem here is how do you compute the b coordinates of a vector x? Okay. So the setup is we take a basis b. So the vectors in B are B1, B2 through Bn. And remember, the order is important. So we fix the order of the vectors in B. So now fix, let x be an arbitrary vector. So how do we compute x relative to B? So the short answer is that we solve the vector equation x equals c1v1 plus .cn_vn for the variables or the unknowns c1 through cn, right? That's what we're looking for. The c1 through cn are the coordinates of x, right? So let's do a couple of examples. So let's go back to the previous slides on the example 2 there, right? So we have our bases v1 and v2, so 1, 1 and 0, 2, and x is 4, 3, right? And so we are looking for c1 and c2 now, expressing 4, 3, namely the vector x, as c1 times v1, so in this case c1 times 1, 1, and plus c2 times v2, so c2 times 0, 2. And this really amounts to solving the equation whose augmented matrix is the matrix 1, 0, 1, 2 on the left and 4, 3 on the right, on the right column. And this is applicable to more or less all situations where the vectors are vectors in some vector space R to the n. Okay, and this is just a standard row reduction problem, or solving a system of equations problem. You know, you row reduce, etc., and then you find out solution is c1 equals 4 and c2 equals minus 1/2. Okay, so let's go to example 2, which is slightly different in that the vectors are in the space of polynomials, p sub 2. Okay, so remember that p sub 2 is the space of all polynomials in variable x, in the variable x that has degree at most 2. Okay, so b is going to be consisting of 3 vectors: 1, the polynomial 1, the polynomial 1 plus x, the polynomial 2 minus x squared. And let's just assume for the moment, let's just accept for the moment that b is a basis for p2, and we'll address this problem of explaining, or we'll explain the problem of why b is a basis later. Now let x be the polynomial 2x plus 3x squared. Sorry, I have too many x's here, but just distinguish the two x's here. The x vector is different from the variable little x that goes on in the polynomials there. Okay, so we'd like to compute the b coordinates of x vector, and so we solve the equation. X equals, right, c1 times 1 plus c2 times 1 plus x plus c3 times 2 minus x squared. So how do we solve this equation? Well, let's just group the coefficients that come along with the polynomial 1, polynomial x, and polynomial x squared. Right, so you move the 2x plus 3x squared over, so then you get the equation c1 times 1 plus c2 times 1 plus x plus c3 times 2 minus x squared minus 2x minus 3x squared equals 0. So now group the coefficients together. So we're gonna get 1 plus c2 plus 2c3 times 1. So the 1 plus c2 and plus 2c3 is the coefficient that that goes with the polynomial 1, and then plus c1x plus minus 3 minus c3 times x squared equals 0. Okay, so now we obtain a polynomial that equals the 0 polynomial on the right hand side there. Okay, so a polynomial equals the 0 polynomial if and only if all of its coefficients are 0. And just make a distinction here, the 0 between the 0 polynomial and the 0 as the number. Okay. So we have the following system of equations. C1 equals 0. So just notice the C1 is the coefficient that goes with x. So that has to be 0. The coefficient C1 plus C2 plus C3 also has to be 0, and so is minus 3 minus C3. If you solve this system of 3 equations, 3 unknowns, then you clearly get that C1 equals 0, C3 equals minus 3, and C2 equals 2. Okay. And that's it. The coordinates of x now is just 0, 2, minus 3. Right? So x sub b is the vector in R3, and the vector is 0, 2, minus 3. Okay, so in the next slide, so this would be the last topic, and then I'll explain why the basis B in the example I gave above is a basis for P2 in the last slides. All right, so we're going to talk about coordinate mapping and change of coordinate matrix. So let B, V1 through Vn be a basis for vector space V. I think I called these basis vectors B1 through Bn before, but somehow I switched to V1 through Vn. It doesn't matter. So we call them V1 through Vn now. And let X be a linear combination of V1 through Vn, so C1 V1 plus C2 V2 plus dot 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 Cn Vn. So the map that takes x to its b coordinates is called the coordinate map, and the theorem is that this map, so they call it T, so the T of x is x of b as above, is actually a 1-to-1 onto and a linear transformation from V to Rn. I'm not going to give a proof of this theorem. It's not hard, but let me just explain why is this theorem significant. So this theorem is significant because what it's saying is, if you got some arbitrary vector space V, you know, it's whether it's polynomials or functions or anything that such that there is a basis of size n, so just a finite basis of size n, then essentially that vector space V there is essentially the same as Rn via this map T, right? So what any kind of linear relationships between vectors and V, when you look at their images under T, it gives you exactly the same linear relationships between those coordinates of those vectors, right? And so it's going to be important for us in the next slide. So just keep it in mind that, you know, any kind of calculations that you do for vectors in V, you can essentially do the same calculations for the coordinates of those vectors in Rn, and that gives us the advantage in a lot of the calculations because we know how to deal with vectors in Rn better than other vector spaces. Okay. So in particular, if V is Rn, then we can say something about, and so in this case T is a linear transformation from Rn to Rn, okay, and so it is a linear transformation, so it has a standard basis. So we can say something about the standard basis for T. So first of all, let P sub B be the n by n matrix whose columns are V1 through Vn. Okay. Then note that if you multiply P sub B with x sub B, so the coordinates, the B coordinates of x, then that's the same as multiplying the vector, the matrix V1, V2 through Vn with C1, C2, Cn, right? And remember the definition of multiplying a matrix by a vector. You just take the numbers in the vector and you multiply with the columns of the matrix, and then you add them up, and so the result is C1 V1 plus Cn Vn, and that's exactly x, right? Well, B is a basis for Rn, and so the invertible matrix theorem says that the matrix P sub B is invertible, right? And we have the P sub B times the B coordinates of x equals x. That means that you can multiply PB inverse on both sides, and you get that P sub B inverse times x equals x sub B. So this means that the standard matrix A sub T of the map T is exactly the inverse of P sub B. Right? So that's kind of a cool observation. All right. So lastly, let's just address why the basis B that we did in the that we chose in the example before for P sub 2. Why is that a basis for P sub 2? Okay, so we have to verify two things. We verify linear independence, and we verify that it spans. Right. So for linear independence, let's write down the equation for linear independence. So suppose that A times the first vector, so times the 1 polynomial, plus B times the second vector 1 plus x, plus C times 2 minus x squared equals 0. We need to see that the only solution for this equation is that A equals B equals C equals 0, right? So how do we do this? So again, we group the coefficients that go with 1, with x, and with x squared into their own groups. So we get that A plus B plus C times the 1 polynomial plus B times x. Yeah, so there's a typo there. It should be B times x instead of B times x squared, plus minus C times x squared equals 0. Oh, sorry, there's another typo. It should be A plus B plus 2c times 1. Instead of a plus b plus c, it should be a plus b plus 2c times 1 plus b times x plus minus c times x squared equals 0. So now we solve the system a plus b plus 2c times 0. A plus b plus 2c equals 0, b equals 0, and minus c equals 0. Then clearly we get that the only solution is a equals b equals c, right? Right. So you just the second equation already tells you b equals c. Third equation tells you the second equation tells you b equals 0. The third equation tells you c equals 0, and you plug in those values to the first equation. That forces a to be 0, and that's the only solution. Okay, so that's linear independence. For spanning, it's probably a little bit easier to verify spanning using the idea in the previous slide. So use the coordinate mapping. Okay, so what I'm gonna do is I'm gonna map the vectors in B to their coordinates relative to the standard basis C for P2. So the standard basis for C2 is for P2 is C that has 3 vectors, 1, x, and x squared. And it's clear that that this is a linear independent set, and any vector, any polynomial in P2, any polynomial of degree at most 2, is a linear combination of these 3 vectors. Right, so take x to x sub c, and so if x was the one polynomial, then its coordinates is 1, 0, 0, right? Because 1 is 1 times the one polynomial plus 0 times x plus 0 times x squared. And 1 plus x has coordinates 1, 1, 0. 2 minus x squared has coordinates 2, 0, minus 1. Sorry, that's another typo. That shouldn't be minus 2, it should be 2, 0, minus 1. So the question now is whether the vectors 1, 0, 0, 1, 1, 0, and 2, 0, minus 1 span R3. Okay, so remember, we are interested in whether the vectors 1, 1 plus x, 2 minus x squared span P2. And look at the theorem from the slide. As I said before, the coordinate map preserves the all linear relationships between vectors in V and vectors in the Rn, namely those coordinates of those vectors. And so our original question about whether 1, 1 plus x, 2 minus x squared spans P2, the same question about whether the coordinates 1, 0, 0, 1, 1, 0, and 2, 0, minus 1 span R3, those two questions have the exact same answer. Okay, so if you can answer the question for the coordinates, then the same answer would hold for the original vectors. And so that's what we do with the coordinates here. And so you can verify this easily, that the vectors 1, 0, 0, 1, 1, 0, 2, minus 0, minus 1 actually spans R3, because you just put them into a matrix, a 3 by 3 matrix, and then verify if there's a pivot in every row. We've done this many times, and the answer is yes, right? So that means that the original vectors 1, 1 plus x, 2 minus x squared spans P2, and we're done.